Welcome back to the video lecture series on pattern recognition. This is Josna Devi Bodapati, Assistant Professor, Department of CSE, DFSTR. So in the previous lectures, we have discussed what pattern recognition is, what are the applications of pattern recognition, and what is the basic workflow of pattern recognition system, and all these things, right? So in addition, we also discussed some of the mathematical preliminaries that are required to understand the pattern recognition systems. So as part of that, so today we'll be discussing probability and statistics. So basically, we need to have familiarity of probability and statistics to get the better understanding of the pattern recognition systems, or to get the detailed and in-depth understanding of the pattern recognition systems. It is very much important to have the knowledge of probability and statistics. In this lecture, we'll be discussing what probability is, what is the need for it, and give you basic intuition why should we go for probability and statistics as part of the pattern recognition algorithms. So then I'll explain what conditional probability is, then what's Bayes' theorem, so followed by the random variables, so both the discrete and the continuous random variables. So what are they? We'll discuss that. So then we'll be discussing various probability distributions like Bernoulli distribution, Gaussian distribution, binomial distribution. So then we'll see what is statistics about these probability distributions, like mean, how to compute the mean of the variable, the mean of the distribution, and the variance. So all these things and their properties we'll be discussing. So let's start our session. So by getting the intuition of why a machine learning expert or the pattern recognition scientist should understand the probability and statistics. Why should we have the knowledge of it? So let's see. So consider, D is a set of examples. So consider, D is the data set that we are taking, that is used for the training data, and which is the data set usually contains the set of samples and the outputs, so the objects along with the labels, right? So that is what constitutes the training data, and we'll be having usually n number of samples. Capital N represents the number of samples, and when we design the model and using this trained data, and while testing, so we'll be giving this, the input, test input as X star, and we are expecting the output from this model, that is Y star. So that's what we do while doing the testing. So in that case, so for the given X star, so what is the predicted value by this model? So that's what Y star is. So this is uncertain. So, and we are, while training the model, we are making certain assumptions. So the assumptions are, say for example, the data is of IID samples. This is known as IID samples, means independent and identically distributed. So we are assuming that the data is coming from a distribution called as IID. So that is, it is representing all the representation samples of the population. So with that assumption, so we train the model. So that's what one assumption we are making. So and also the model what we are getting is also making certain assumptions. So like for example, the parameters, if you consider, so theta are the parameters for a given model, then we are making certain assumptions on the model also. So that is, on the parameters you are making the assumption, on the input data and on the predictions you are making certain assumptions. So consider the case of curve fitting. So curve fitting is basically a mapping of the input data to the output data. And in the simplest case, in the linear model, so consider that you are using the model y equal to f of x given theta, where your model is represented with the, using the equation theta naught plus theta 1 into x, because it's a linear model. So in that case, so what values of this theta naught and theta 1 is the best values, so that you are making certain assumptions, right? So here, if you consider this discussion, so whatever you are making in this case of pattern recognition systems, there are many assumptions you are making. So you are assuming about the training data, you are making assumptions about the model, you are making assumptions about the parameters. So these are all the assumptions you are making. So now when you make some assumptions, there is underlying uncertainty. So the uncertainty is related to the data. So while collecting the data, you are making the assumption, and so while estimating the parameters, you are making some assumptions, and while designing the model, that is the hypothesis you are designing, there also you are making some assumptions. So these are all the assumptions you are making. When you are making some assumptions, there lies an uncertainty, right? So when there is an uncertainty, and this uncertainty can occur both in the inputs and outputs. When you collect the data, so you are collecting the data from the real world, and you are assuming that whatever the data that is available with you is the accurate data, right? So that's what one of the assumptions you are making. And how to deal with this uncertainty? Whenever there is an uncertainty, the term that comes to your mind is the probability, right? So that's where we need to have the understanding of probability. So that's why we should have the understanding, knowledge of the probability. So to understand in detail of the pattern recognition systems, to deal with the uncertainty that is underlying in the parameters, in terms of the parameters, in terms of the model, and in terms of the input data. So why we should have the knowledge of probability is, so probability basically, it allows us for the quantification and manipulation of the uncertainty. So that's why we need to have the knowledge of probability. And also it allows us to make optimal predictions. So even though we are having only a representative, a few set of examples, so we can assume that so the whole population is available with us, and we can design the model. So that's another advantage of using probability. And probability, in addition, forms the foundation for the pattern recognition. So that is how probability forms the foundation for the pattern recognition systems. So I hope now it is clear for you why we should have the knowledge of probability and statistics. Now let's see the terminology, the basic terminology of probability. So let's start with the random experiment. So what the random experiment is? So random experiment is basically, so if you consider wherever there is some, wherever the outcome is not certain, you can consider that as a random experiment. And for example, if you consider the dice throwing, so when you throw a dice, so you cannot certainly say that, so the output will be a 1 or a 2 or a 3, so you cannot predict that, right, certainly. So wherever there is an uncertainty in the outcome, so such kind of experiments are called as random experiments. And now, so let's see what the outcome is. So outcome is the result of an experiment is called as an outcome. Say for example, when you throw a dice, then the outcome would be either a 1 or a 2 or 3, 4, 5 or 6, right? So that is how you can define the outcome of an experiment, and it is represented with small omega, whereas random experiment is represented with the capital E. And you can even consider the outcome of the event throwing a coin. So the outcome would be a head or a tail. So that's how you can define outcome. And now let's see sample space. So sample space means whenever you perform an experiment, then what are all the possibilities of that experiment? So that constitutes the sample space. Say for example, when you are throwing a dice, in that case, what are all the possible outcomes? So these are all the set of possible outcomes of the throwing a dice, right? So in that case, this constitutes the sample space for the throwing of a dice experiment. So that's how you can define sample space. Now let's see what is an event. So event is a subset of the sample space that is of our interest. Say for example, when I throw coins, I am interested only in the event of getting a head. So in that case, getting head in the coin cost, I can define that as an event. Or consider the example of getting an odd number when I throw a dice. So in that case, so I am not interested in 2, 4 or 6, right? So I am interested in 1, 3 or 5. So now I can define, so the event as the subset of the sample space and which is of our interest. So that is how you can define an event. Now let's see what probability is. So consider this example. So when you throw a dice, when you roll a dice, so getting a 4 is of event that is I am interested in. And what is the probability of getting a 4 on the dice rolling is So out of the 6 possibilities, so when I throw a dice, then there is a possibility of getting any of these 3 numbers. And I am interested in only this event. So out of this, so the total number of possible outcomes are 6, and out of these 6, I am interested in only one event, that is my event, the favorable event. So that is how I can say that this is the probability of this event. So the event I am interested is getting a 4 when I roll a dice. So that is how you can define the probability. So basically you can say that, so what is the fraction of favorable outcomes, so out of the total possible outcomes. So out of these total possible outcomes 6, I am interested in only the favorable outcome, that is only 1, right? So that is how the probability of this event is 1 by 6. Say consider for example another example. So rolling a dice and I am interested in getting a even number. So how do you define the probability of that event? So again, the possible outcomes are 6. So that's why in the denominator it is 6. And the favorable outcomes are, so either 2 or 4 or 6. So I am interested in any of these 3, right? So 3 are the favorable outcomes. So the probability of that event can be defined as 3 by 6. So that's how I can define the probability of any event. The favorable outcomes, right? The number of possible outcomes. And now let's see, so some of the axioms of the probability. You must have studied all these things in your 10th standard or even plus 1 or plus 2, but just you can have a review of this. The probability of an event A is always, so in the range of 0 to 1 inclusive. So it's never out of this range. So if you consider the probability of the heads when your experiment is tossing a coin, in that case, if your interested event is probability of getting a head, in that case it is your probability is 1 by 2, so which is in this range, right? So that is how your probability is always within the range of 0 to 1, both inclusive. And the probability of the sample space, where S is a sample space and the probability of sample space is 1. So consider the same coin toss example. So what is the probability of getting a head in the event? So it is half. And what is the probability of getting a tail? It is half, right? And what is the possibility of getting the total sample space? The sample space in this event is, in this experiment is both tail and head. So in that case, so the probability of the sample space is equal to half plus half, which is equal to 1. So that is how the probability of the sample space is always equal to 1. And if you consider A1, A2, AN or the mutually exclusive events. So mutually exclusive events means so they cannot happen at the same time. So consider the same example of coin tossing. So coin tossing is the experiment, and in that case, so I can either get a tail, I can either get a head. I cannot get these two events at the same time. So in that case, I can say that these are the mutually exclusive events. So when head comes, then tail will not come, right? And similarly, when tail comes, head will not come. So that is how these events can be called as mutually exclusive events. So when the events are, so you consider A1 to AN are such mutually exclusive events. So in that case, the probability of intersection of these two events is 0. So it's very simple to understand, right? So say for example, probability of getting a tail and a head. So can you get a tail and head at the same time? It's not possible. So in that case, the probability of this mutually exclusive events together is 0. So here you can see in this figure, so A1 is an event, so this is the total sample space, and A1 is an event, and A2 is another event, A4 is another, A3 is another. And all these events, they occur only one at a time, so they cannot overlap. So such events are called as mutually exclusive events, and the intersection of any of these pair of events is 0. So that's how you can define it. So when you consider the mutually exclusive events, in that case, the probability of union of those events can be simply the sum of the probability of mutual events, because the intersection of these events is somehow zero. That's why the union of these events together is equal to the summation of the probabilities of the individual events. Now let's see what the independent events are. So independent events are the events which occur independently. That means one event does not have any effect on the other event. Say for example, so consider these two events. So one is coin tossing and the other one is throwing a failed dice. So consider the example of tossing a coin and throwing a failed dice. So in that case, getting a head on the coin toss will not affect the getting a 5 on the dice. So these events I can call them as independent events. So independent events are the events to which one event occurrence will not affect in any way the occurrence of the other event. So simple example is you are taking the coin toss example and the die rolling example. So both together you are doing, and getting a head on the coin will not affect in any way on the getting of 5 on the dice. So that's how you can define independent events. So in case of the independent events, so probability of A intersection B is equal to probability of A into probability of B. So in the case of mutually exclusive events, so the occurrence of these events together is 0. But in this case, it's not 0, it is probability of A into probability of B. That is how you can define the independent events. And now let's see what the conditional probability is. So conditional probability can be defined as, so one event is happening and we are assuming that already another event is already taken place. So that is probability of happening of the event A we are considering, but we are assuming that, or we are already given the information that, so the event B is already occurred. So you can say that it is probability of A event B. So the event B already occurred and the probability of A you are now considering. So such probability is called as probability of A given B. So remember, so you should never say it as probability of A by B. So there is nothing like probability of A by B. You should call it as probability of A. Now let's see an example. So consider the an example for the conditional probability. So in the deck of cards, so getting the card ace. So given that another ace is already taken. So what is the probability of getting an ace given that already one ace has been taken? And there is a confusion that this event is happening without any replacement of the first ace. So you are taking the ace first, and then what is the probability of getting the ace the second time? So such probabilities can be considered as conditional probabilities. So now you can see probability of A given B. So in this case, it is, how should you call it? It's probability of A given B. That is the terminology that should be used. Probability of A given B is defined as probability of A intersection B by probability of B. So simply it is the probability of happening of B. And this refers to the probability of A and B together. So what is the probability of these two things are happening together? And now this can be considered as, given the condition that B has already taken place, what is the probability that A can happen now? So that is how the conditional probability can be computed. So now let's see, based on the conditional probability, basically we can derive a useful theorem called as Bayes theorem. So Bayes theorem is very, very important for the pattern recognition applications. Now let's see what the Bayes theorem is. So now consider the conditional probability. The conditional probability just we discussed, probability of A given B can be defined as probability of A intersection B by probability of B. So remember, this is given A given B. This is fraction by A probability of A intersection B by probability of B. And now, so define the other way also, probability of B given A. So probability of B given A. So based on this, you can write probability of B given A also. Probability of B given A is equal to probability of A intersection B by probability of B. So now, so let's take probability of A intersection B from here and also take probability of A intersection B from here. So these two terms are common, right, in both the equations. Now, from this equation, I can say that probability of A intersection B equal to probability of A given B into probability of B. So that I am writing here, probability of A given B into probability of B. What is this? This is equal to probability of A intersection B. So that is from the first equation. And now from the second equation also, I can write probability of A intersection B is equal to probability of B given A into probability of B. So now these two you are multiplying together and that is equal to the probability of A intersection B. So now, so you got this equation, right? So once you get this equation, so this is the A intersection B is equal to probability of A given B into probability of B, which is equal to probability of B given A into probability of A. So now simply you had to compute probability of A given B. So probability of A given B can be computed as this is equal to probability of B given A into probability of A by, so you just move this probability of A this side. So now this is called as the Bayes theorem or simply the Bayes rule. So this is basically called as, we'll see that. So this is called as probability of, so in Bayes theorem, probability of A given B is known as the posterior probability. So try to understand, it's no more a conditional probability. Now this is called as a posterior probability. So while making the decisions and all in pattern recognition or the machine learning algorithms, so this posterior probability is very, very useful. And the whole part of your second unit will be discussed only on this Bayes theorem and the posterior probability. So understanding this concept is very, very important. So this is what the posterior probability is. The posterior probability can be computed as probability of A given B equal to, so the likelihood into the probability of B given A into probability of A by probability of B. So this is just whatever we have seen in the previous slide. So from the conditional probabilities, so both the conditional probabilities we have derived this Bayes theorem, probability of A given B and probability of B given A. So from that we got probability of A intersection B from both the equations. Then we just equated these two equations and then finally we computed probability of A given B. So that's what the Bayes rule is or the Bayes theorem is. So what the Bayes theorem says is the posterior probability of a variable is equal to the likelihood. So this term is called as the likelihood. So we'll see soon what the likelihood is, how to compute the likelihood and all. So in detail we'll be discussing in the second unit, but this is kind of a foundation course. So now this is the likelihood of the variable and then this is called as a prior probability, and whatever is available on the denominator it's called as normalizing constant. So basically when you consider the posterior probability without this normalizing constant also you can compute the posterior probability. But the problem here is the likelihood value do not have any range. So it can go up to any value. And now the prior value is a probability basically. And if when you multiply these two values, then it can take any value. And to make the posterior as a probability, so instead of getting a value, so you should make the posterior as a probability. So what you are doing is you are basically normalizing that so that your posterior term will become a probability. And we'll see what this normalizing constant is now. So consider the events, intersection of the events. Now consider there are three events, A1, A2 and A3 are the three events. Now I am interested in the intersection of all these three events. So I am interested in the events A1, A2 and A3 together. So that is the event B, which is an intersection of these three events. So when I consider the intersection of these three events, I mean I am interested in, so this area I can define it as A1 intersection B, and this portion which the event B and A2 are intersected, that I can call it as A2 intersection B, and this portion I can call it as A3 intersection B, right? So now the probability of this whole event B, can I call it as summation of the probabilities of probability of A1 intersection B, probability of A2 intersection B and the probability of A3 intersection B. So if you sum up all these three probabilities, what you get is the probability of B. So probability of A1 intersection B plus A2 intersection B plus probability of A3 intersection B. So now you have the probability of B. So now let's continue. So based on the conditional probability, we already discussed that. So the conditional probability is equal to conditional probability of B given A is equal to A1 intersection B by probability of A1. So from that, so I am deriving probability of A1 intersection B and I am replacing that with this. So we just discussed in the previous slide, right? So here if you observe, so probability of A intersection B can be either this or this. So based on that, so I am defining it as, so now I am replacing this A1 intersection B with this, and similarly A2 intersection B with this, the likelihood into prior, and A3 intersection B with the likelihood into prior. So now I got the probability of B in terms of the likelihood and the priors. So now can I say that, so if you have 3 events, it's the summation of the likelihood into prior terms of all the 3 events. So if you have n such events, and then the probability of B can be defined as the summation over all these n events. So where you consider the likelihood and the prior, the multiplication of these 2 values. When you are summing them up, and that's how you are getting the probability of B. So that's what is basically your marginal probability of your what you call it as the Gaussian theorem. So that's what the normalizing constant, or you can even define it as the normalizing constant, marginalization probability. So now consider, so from the previous 2 slides, we are just trying to combine the previous 2 equations. So probability of AI given B can be defined as probability of B given. So based on the Bayes theorem, so we are writing this probability of AI given B. So if you assume that AI is one particular event, so B is the sample. What is the possibility that the event B is belonging to this class? So that's what the posterior probability basically tells. So probability of AI given B is equal to probability of B given AI, the likelihood, then the prior of the class, and then this is the marginal probability. And we just have seen that the prior probability can be computed as the summation of the probabilities of the product of the likelihoods and the priors of all the events. Now, in this equation, if you substitute this, so your Gaussian theorem or the Gaussian rule will be like this. So probability of AI given B. So the meaning of this is, what is the probability that this event B, this value B is belonging to, this B is belonging to this class AI. That is, a posterior probability is equal to the likelihood into prior by the marginalization. So that's what the Bayes theorem is. And now let's see how Bayes theorem is helpful in the pattern recognition systems. So I just give you the overview. In the second unit, we'll be discussing in detail. So just because we understand what Bayes theorem is, I feel it is easy to understand. So how it is useful in the pattern recognition systems. Say for example, we have Wj. Say for example, Wi is the class, is the ith class, and I have, say for example, n number of classes, and Wj is the jth class, and in that, and we consider x as a feature vector. And what we are going to compute is, I need to understand what is the probability that this feature vector x is belonging to this class omega j. So how do I compute that? This is nothing but the posterior probability that's taken from the Bayes rule. So the posterior probability can be written like this, right? So your likelihood term to the prior of the class, and this is the marginalization over all the classes. Now, if you consider this, or simply you can write as probability of capital X itself. So which is both are the same. So these two are the marginalization probabilities. So that is how you get the posterior probability for the jth class. And similarly, if I have n classes, I will find the posterior probability for all the classes, all the n classes. And to whichever class the posterior probability is maximum, to that class I will be assigning the example. So now I am given this example and I want to make a decision. So to which class, what is the probability that this example is belonging to? So this class, jth class. And my decision should be, so I should be assign this feature vector x to the class which is the best possible class. right? So in that case, what I do is I compute the posterior probabilities for all the classes with respect to all the classes. Say for example, there are two classes. In that case, what I do is I will compute probability of omega 1 given x, and I will compute probability of omega 2 given x. Assume that because it's a probability, the summation of the posterior probabilities across all the classes is equal to 1. So that assume that the probability of this is 0.4 and obviously this will be 0.6, right? So now, so I will assign this feature vector x to the class to whichever the posterior probability is maximum. So if you consider this 0.4 and 0.6, so 0.6 is greater, right? So the better thing is you assign this example x to the class which is having the maximum probability, maximum posterior probability. So that is how this Bayes theorem is very much useful in the pattern recognition system. So that just for your sake of convenience, so I just listed out what probability of omega I is. So in this case, probability of omega I is the prior probability of the ith class. And what is probability of omega I given x? So what is the meaning is simple. So meaning is you can consider this as what is the probability that this example x is belonging to the omega I, that is the class I. What is the probability that this feature vector x is belonging to the class I? And now what is this x given omega I, and this is called as a posterior probability, and this is called as the likelihood. So here you can see this is the likelihood term. Probability of x given omega I. So the likelihood you need to identify. So how do we identify the likelihood of the given example? So we'll shortly discuss that. And then the probability of x. So it's a marginal probability. So once you get the likelihood of one particular class, so once you know how to identify that, similarly you need to compute the likelihood across all the classes. And you just sum them up, so that gives you the normalized probability or the marginal probability of x over all the classes. So that is how the Bayes theorem is very, very important to make certain decisions in the pattern recognition systems. And now let's see, so an example can be solved using the Bayes theorem, the real-time example. So now consider, so in a country, 51% of the people are male. So given this data, so we need to identify something. Let's see what is that. So given that 51% of the population are males, so I consider that probability of male. So male is, I consider m for males. So the probability of m is given. It is equal to 51% means in terms of the probability you can write it as 0.51. And now, so when the probability of male is 0.51, then simply you can write the probability of females as 0.49 because the sum of probabilities either male or female, right, the gender. So that is how you can figure it out. So you can, so from the given data, you can get probability of female also, which is 0.49. And now, the data that is given is in addition to this, 9.5% of the males smoke cigars. So this you can consider it as conditional probability. So what is given? The males smoke cigars. So given that the person is a male and the probability that he smokes cigars is equal to 90.5%. 9.5% means in terms of the probability you can write it as 0.5. And what is the other thing that is given? So 1.7% of the females smoke cigars. So given that the person is a female, what is the probability that he smokes cigar is equal to? It's given as 0.17. So 1.7 equal to 0.17. So now we have the data. So the prior probabilities, so now you understand, right? So you can relate this to the Bayesian rule. So this is the prior probability of, I have two classes, female class, male class. The prior probability of male class is 0.51 and the prior probability of female class is 0.49. And now, so this you can consider it as conditional probability. So given the male, so what is the probability that he is smoking? As it is 0.95. And given the female, what is the probability that she is smoking? It is 0.17. And now, so what has to be computed? So using this information, you need to identify the probability that the person smoking cigars is a male. So given that the person is a smoking person, he smokes a cigar, and what you need to identify is, so he is a male person. So now what is this? This is posterior probability. So now I have the likelihood for both the classes, I have the prior probability for both the classes, and of course we know how to compute. So we know how to compute the posterior probability, right? So instead of taking the female, I just taken the probability of male complement, right? Now let's see how do we compute. So this is the data that is taken from the problem itself, and that's a formula for the posterior probability. And now, so this is how you can compute the posterior probability. So the probability that is asked for is, so given the person is smoking, what is the probability that he is a male person? Okay. So now just whatever the values you have, you just substitute them in this formula, the posterior probability, and finally you get that. This to the 0.85. To the 0.85. That is 85% of the male people, the smoking people are male. So that is how you can find you can make use of the Bayes theorem and actually can solve a lot of problems. And now let's see what are the types of probabilities. So the types of probability space. What are the different types of probability space that are possible? So we just defined this as a sample space. So sample space is nothing but the size of the number of possible outcomes. That's what the sample space is. Where this is sample space and the number of possible events is the sample space. And now, so the sample space can be either discrete or it can be continuous also. There are two possibilities. The sample space can be discrete or continuous. So what is the sample space basically? So given the coin tossing example, the sample space is head and tail. So now this is the sample space, right? So given the like rolling a dice problem, now the sample space would be 1, 2, 3, 4, 5, 6. These are the possible outcomes. So in this case, so here the number of outcomes are 3. So here the number of outcomes are 3, 3, 6. Right? So whenever the number of outcomes of the event of the experiment are finite, so here you can see it's countable, it's 2. That is, it is finite. So the size of your sample space is finite, means you can consider such sample space as a discrete space. Right? When it is a discrete space, then your analysis involves only the summations. And the example for the discrete space is the coin tossing example. And now consider, so here also it's a finite number of events in your sample space, so that is 6. So that is also finite. So it is also an example for the discrete space. Say for example, so the weights of the persons. So what is the possibility of the values for the weight of the person? So weight of the person can be 40.8, 40.9, 62.5, right? So it can be any value in between some range, right? So even that range also I can't say exactly, but usually it's something like, so 2 maybe 200 or 500 I can say. So in this range, it can take any possible values. Is it discrete now? It's no more discrete. So even if I say 40.8 and 40.9, so there is a possibility of getting another value here also, right? So that is how this kind of values are called as continuous values. And so when you are samples, now can you count how many possible values in this range? It's infinite. You cannot count it actually. So that is the size of your sample space is infinite. When your size of the sample space is infinite, then such sample space is called as continuous space. So when your sample space is continuous, then your analysis, probability analysis involves integrals. So in the case of the discrete sample space, your analysis involves summations. In the case of the continuous sample space, your analysis involves integrals. And of course, I just gave the example, that is the weight of the people. So that is how you can consider, depending on the sample size of the sample space, you can consider the sample space as a discrete sample space and the continuous sample space. If it is a discrete sample space, then your analysis involves summations. If it is continuous sample space, then your analysis involves integrals. So let's have a look at that. So now let's consider what random variables are. So random variable is a kind of X. You always represent with capital letters. So for this case, we are using capital X to represent a random variable. And what this random variable does is it basically maps the events in your sample space to a real value. So that's what the random variable is. Now let's see here, this is the sample space and these are all the events of the sample space. Okay, so consider these are the events. Now, so this event is given some association with the real value. So this is the access for the real values, the scalar value. So now this event is associated with some real value, this event is associated with some real value. So that is what the random variable is. Random variable basically so maps the output events of the sample space to some real values. Say for example here when you toss a coin 3 times, then X is a random variable, so which indicates the number of heads that turns up. So that's what the random variable I am indicating. So now the possible values for this random variable could be either it is a 0 or a 1 or a 2 or a 3, right? So now in this case I can say that probability of, so X is my random variable and it can take a 0. So now I can say what is the probability that X equal to 0. So now I can compute this probability. Or I can say that what is the probability that X equal to either 0 or 2. So that is I am interested in the event. So it's actually this random variable is indicating an event that I am interested in. So now here if I say 0, 2, in that case I am interested in getting either 0 heads or 2 heads. That is even number of heads I am interested in. So in case of the coin is tossed for 3 times. So that's about the random variables, and the random variables can be of 2 types, discrete and the continuous. So in case of the discrete random variables, the values are finite, the sample space is finite, and in case of the continuous it is infinite. So you cannot count the number of possible outcomes. And for example, you can take, so it's dead or alive in case of the discrete space, and the pass or fail, or for example the dice, outcomes of the dice, all these things comes under the discrete random variables. And in case of the continuous random variables, I can consider all the possibilities for the continuous values. So you can consider height of a person, weight of a person, or the speedometer, or even so the length. So all these indicates the random variables are the continuous random variables. So now we should understand if the random variable is discrete, then so we need to analyze the summations, right? So that's what we discussed in the previous slide. So if the random variables or the sample space is continuous, then your analysis should be something related to integrals. Now let's see why should we go for the summations of the integrals. So consider the discrete sample space. So in case of the discrete sample space, so the probability mass function and the probability cumulative distribution function. So these 2 terms are defined when your distribution is a discrete distribution. So at both so the probability of a particular the random variable at a particular value is defined. So when your distribution is a discrete distribution, so I can simply say that what is the probability that the random variable, so the random variable actually indicates the event of my interest. What is the probability that the random variable, that is the event is having a 1 value. Say for example, when I roll a dice, what is the probability that getting a 1? So in that case, I can say that what is the probability of getting a 1, right? So you can compute the probability of that. It's simply 1 by 6. So that is how this is defined as the probability mass function for the random variable in case of the discrete distribution. And similarly, cumulative distribution. So in case of the cumulative distribution, your random variable will take a value and you are counting the probability of getting that value, including all the values that are less than that. So that's what the cumulative distribution is. I think this picture will give you a detail. So now consider this. So this gives you better understanding of what EMF is and what CDF is. So probability mass function and cumulative distribution function. So these are the EMF and CDF for the event, for the experiment of 3 coin toss. So the coin is tossed for 3 times. And I am interested in getting a heads up. Okay. And in that case, there is a possibility of getting either a 0 head or 1 head or 2 heads or 3 heads. Right? Because I am throwing it for 3 times. And how many times? The heads up. So that's what the event that I am interested in. So there is a possibility of the random variable can take either a 0 or 1 or 2 or 3. And in case of the probability of x equal to, so here you can see that this is equal to the probability of the random variable x is taking the value of 1. So what is the probability that you are getting 1 time heads up? So that's what this means, right? So it is 3 by 8. And similarly, probability of x equal to 0 is 1 by 8, and probability of x equal to 2 is the same, 3 by 8, and probability of x equal to 3 is also 1 by 8. So that's how the probability mass function can be computed. And consider this probability cumulative density function. So cumulative distribution function can be defined as the probability of getting that and also all the below events. Say for example here, if I say probability of x less than or equal to 2, that indicates what is the probability that I am getting either a 2 or a 1 or a 0. So all these 3 probabilities together I can consider. So if you consider 1 by 8 plus 3 by 8 plus what is it? 3 by 8. So these 3 together you can compute and just sum them up. That gives you probability of x less than or equal to 2. So that's how the cumulative distribution function can be defined. Now let's say why should we go for the continuous distribution and what is the necessity for the probability density function. So when the distribution is discrete, then you can define the probability mass function and the probability cumulative distribution function. But in case of the continuous distribution, you cannot define PMF or the CDO. In that case, you have to define what you call it as probability density function. So let's see, why do we need to have the probability density function? Why not the probability itself? The reason is very simple actually. So consider the temperature example. So your random variable x indicates the temperature of the day. So the temperature, so your model is going to, or your random variable is representing temperature of a day. So now the random variable, what is the possible range for the random variable? It can be any value, maybe something like 5 to maybe something like 45, right? So if I assume that the minimum temperature is 5 degrees and the maximum temperature is 45 degrees. So now the random variable x can take any of these values in this range. Can I say that, so the possible values are only 5, 6, 7, 8, 9, only the integer values within this range? In that case, it is final. So can't we have the temperature as something like 6.7 degrees, 7.9 degrees, 42.1 degree, and even I can't even see that it is 42.1 and 42.2 are really possible. You can even have 42.11 also. Even you can have 42.111 also. So that is how you cannot say that it is discrete. You cannot count the size of the sample space. So in that case, you can say that the random variables are continuous. So when your random variable is continuous, it is not possible to find the probability of the random variable. Say for example, can I say that what is the probability of x equal to 45? I cannot say that, because so you have infinitely many values within this range of 5 to 45. So if you say that the probability at a particular value, that is not valid at all. So because it's infinitely many values. So your PMF is not valid in case of the probability, in case of the discrete distributions. So then in that case, we define what you call it as probability density function. So in case of the continuous random variables, you need to define what you call it as probability, probability density function. And the probability density function can be defined like this. So your variable is this, then so your probability, that means you are considering the probability within the range of a comma b. And in that case, you are considering the integral of a to b, integral, the lower limit is a, upper limit is b, and f of x dx. So in that case, you can consider it as f of x minus b. So that is how you can compute the probability density function. So for the continuous random variables. Continuous random variables means which are not discrete. So you cannot say that these are the number of values within the range. There are infinitely many values within the range. So the possible values the random variable can take is infinitely many or infinite. So now consider this. So say for example, the probability that the value is between 12 and 14, I want to find. So say for example, in the temperature case, what is the probability that, so the temperature value can take the value 12 and 14. So in that case, I need to identify the area between this. So because this is the whole possibility, whole range that is possible within this range, and this is the overall curve that is representing the probability distribution, and your range of these values is representing this part. And in that case, so how do you find the area under curve? You have to use the integration, right, to find the area under curve within the range. So that is the reason why we need to go for the integrations in case of the continuous distributions. So already we have taken enough examples. Maybe you can consider another example. So the time taken to accomplish a task. So you can't say that so exactly at this point of time, right? So that's why it's continuous. So whenever the distribution is continuous, you need to go for probability density function, not the probability mass function. The probability is not defined at a particular value in case of the continuous distribution. The expectation is basically defined as the mean of the probability distribution. So the expectation of x is represented with the mu symbol mu, and it represents the mean value of the probability distribution. So for the discrete variables, the mu value can be defined as expectation of x equal to, so whenever it is discrete, the analysis is done in terms of summations, right? So that's why it can be defined as summation of x into f of x, or you can even say p of x itself. So that's how the expectation value is defined in case of the discrete case. In case of the continuous variables, so the mean of the random variable can be defined as, so here you should go for the integrals. That is the reason why the analysis is done here. In the case of the discrete case, summations, here the analysis is done in terms of the integrals. So now it becomes integral x into f of x. That's how the mean can be defined for the discrete variables and the continuous random variables. Now let's see the random variable x, which is representing the number of people that are before you in the line. So basically you are going for a post office at lunchtime, and usually there will be a queue in the post office, and so you need to identify on an average how many number of people would be there in the line before you at any point of time. So that's what the problem is. So the data that is given to you is, so the probability for having 0 people before you is 0.1, and similarly the probability that one person is 0.5. Similarly, the probability that there are 2 people in the queue before you is 0.3. Similarly, the probability that there are 3 persons before you in the line is 0.5. And given this data, you need to identify on an average how many people would be there at any day before you in the queue. So now let's see how do you solve that. So you can use the expectations formula and you can compute this. So simply how do you identify? 0 into 0.1 plus, so basically expectation of x, the random variable can be defined as x into f of x is summation of x into f of x, right? So 0 into 0.1 plus 1 into 0.5 plus 2 into 0.3 plus 3 into 0.2. So when you sum up all these values, so 1.2. So that means at any day, on an average, there will be 1.4 people that would be there in the queue before you, your turn comes. So now let's see what are some of the properties of the expectation. So expectation of the expectation of a random variable. So if you take the expectation of the random variable and again the expectation, that itself indicates the expectation of x itself. Now the expectation is applicable. So the linearity is applicable for the expectation. That is, expectation of x plus y is equal to expectation of x plus expectation of y. So here in this case, x and y are the random variables, and expectation of x plus c can be defined as expectation of x plus c, where c is a constant and x is a random variable. So expectation of x plus c is equal to expectation of x plus c. So now expectation of ax plus by equal to a into expectation of x plus b into expectation of y. So that is how you can, these are the properties that holds good for the expectation. So that will be useful for you at some point of time in this course. So these mathematical courses are all designed such that, so it will be helpful for you to understand any of the pattern recognition courses or the machine learning or the AI courses. So not only this pattern recognition course that we are teaching, so if you understand all the mathematical preliminaries that we are teaching, not only useful for this course, you can register for any of the any of the pattern recognition or the machine learning course. It would be very easy for you. That's how we designed it. Now, it holds the non-negativity property also. That is, if the random variable is taking the value that is greater than or equal to 0, and definitely the expectation of the random variable is also a positive value. And also, if x is greater than or equal to, the random variable value is taking a positive value, and if expectation of x is 0, then you can say that the probability of x equal to 0 is 1. So that is how these properties can be defined. And also one more important property, if x and y are independent, then you can say that expectation of xy equal to 0. So you are taking the product of these two variables and then you are applying the expectation of that. So that's equal to 0. And now let's see, so the variance. So variance and standard deviation. So these are the statistical measures that are required for any probability distribution. So we have just discussed what the expectation is. Now let's see what variance and what standard deviation is. So variance is actually gives a spread of it, gives a measure of the spread. So how far you are from the mean. So given the distribution, so given a value, how far you are from the distribution. Say for example, I got 50 marks and the average mark of the class is, say for example, 60 marks. So how far I am from the mean? So that value gives the variance of the random variable. Now let's see what some of the properties. So how to identify variance of the random variable? So variance of the random variable can be defined as variance of x, or simply you can say sigma square. So the sigma square equal to expectation of x minus mu whole square. That is, you just subtract the mean from the variable x, random variable, and take the square of that, then apply expectation of that. So that gives you the variance of the random variable. And simply you can say that, so when it is expectation of x minus mu whole square, right? So that's what is. So that's what the variance is. Now from this you can simply say that how do you, so if you consider this as a single variable x, what is expectation of x? Expectation of x is the summation of x into probability of x. Now in that case I can simply say that x minus mu whole square into probability of x, right? So that is how I can define. So the same way I have defined, and if you consider this, so I can say that if you expand this, so it is equal to expectation of x square minus x square. And in the case, this holds good for the discrete variance. And let's see how we compute the variance for the continuous case. So for the continuous random variables, variance can be defined as integral a to b x square f of x. So of course you need to use integrals minus b square. So that's how you can define variance. And now what standard deviation? So standard deviation is just the square root of your variance, and it's defined as sigma itself. Variance is defined as sigma square, whereas variance is the standard deviation is defined as sigma. So now let's see this example. So see this figure. So here I have two distributions. This is one distribution. So we have two distributions here. So this is the distribution with the smallest standard deviation. So based on the figure itself, you can understand, right? So the width of the distribution is very small. Whereas if you consider this, it's having wider distribution. So it's taking more values in the range. That's how the spread is more. So that's how actually variance is a measure of the spread. Variance and standard deviation both gives the measure of the spread. And now let's see what are some properties of the variance. So variance of A, that is if you consider A as a constant, A, B and the constants or the scalars, and X and Y are the random variables, so the following properties holds good for variance. So variance of a constant is always defined as 0. It cannot be defined. And now variance of x plus y is equal to, can be defined as variance of x plus variance of y, where x and y are independent variables, independent random variables. In that case only you can say that variance of x plus y equal to variance of x plus variance of y. And now variance of a into x, where a is a scalar, x is a random variable. In that case I can define this as a square into variance of x. And let's see what variance of x plus a is. Variance of x plus a can be defined as simply variance of x itself, because a is a scalar. And now, so variance of ax plus b can be defined as a square into variance of x. Because on the scalars, variance is not defined, 0, right? It's defined but it is 0. And similarly, variance of ax plus by can be defined as a square into variance of x plus b square into variance of y. So, and this also holds good only when x and y are independent. So, x and y are independent, in that case only the linearity of variance is replicable. And now let's see what covariance is. So far we have seen what expectation is, what variance is, what standard deviation is. So if they are scalar values, then that is how we define the variance. But in case of the multivariates, say for example, x is defined. So here in this case, x is defined as x1, x2, so on, xn. It's a multivariate. So in that case, how do we define the covariance? In that case, the variance of the variable is called as a covariance. It actually measures the variation in the data. So how do we define that? Is expectation of, it's basically defined as expectation of x minus mu into x minus mu transpose. Because, so directly you cannot say that it is x minus mu whole square. It's no more a scalar. It's a multivariate vector, right? So in that case, I should write it as, instead of this, I can say that. So normally, how do you define the variance? It is x minus mu, expectation of x minus mu whole square. But in case, that is in case of the scalars. But here it is no more a scalar, right? So your variable x is this, which is having a multivariate distribution. In that case, I can define variance as covariance. The covariance of x can be defined as expectation of x minus mu into x minus mu transpose, and which results in a matrix of size n by n. And in that case, so on the diagonal, the principal diagonal, you can see, so they are the variance values itself. And off the diagonal, you can see the covariances. Say for example, if it is x1, x1, x2, and so on, xn. So each cell indicates the variance between the values. On the main diagonal, what you are indicating is the variance between these two values, x1 and x1, right? That's how it is, variance itself. So off the diagonal, so the relation between x1 and x2 here. So similarly, it is x1 and xn here. So they represent the relation between two variables. So that's how you can define where covariance of the random variables. And covariance can also be defined between two different random variables, and it can be defined as expectation of x minus mu x into y minus mu y. So if it is covariance is on the same variable, you can define it as x minus mu into x minus mu transpose. But here in this case, I am defining the covariance between two different variables. In that case, I will define it as expectation of x minus mu x into y minus mu y. And basically, covariance of x comma y can be defined as, so if you so expand this, so x minus mu x into y minus mu x. So in that case, you can write it as x into y, so xy minus x into mu y minus mu x into y plus mu x into mu y. And on that, you have to apply the expectation. And when x and y are independent, so when you derive that, so solve this equation, then so your covariance of xy is equal to expectation of xy minus expectation of x into expectation of y. And we have already seen that when x and y are independent, this value becomes 0. So when this value becomes 0, then your covariance of xy is equal to this itself, expectation of x into expectation of y. So that's how you can define covariance between two independent random variables. So now let's see the pictorial representation of the covariance between the random variables. So here you can observe x1 is or xi is a random variable, xk is another random variable. And this picture shows the correlation between or the covariance, the relation between the variables. What actually the covariance tells you is, so how these two variables are related to each other. So say for example here, so these are moving in the reverse direction, right? So if x1 is taking the small value, xk is taking the large value. And if you move towards the larger values of xi, then if you observe xk value is taking the lesser values. Can I say that there is a negative correlation? So of course, whenever you have this kind of line, either in this direction or in this direction, then you can say that the variables are related. There is a relation between these two variables xi and xk. But here in this case, because they are moving in the reverse direction, I say that the correlation between these two variables is negative. And let's see this. So here if you observe xi and xk, so here there is no much correlation, but it's of minus half. So you can't exactly say that. So whenever it is increasing, so whenever xi is increasing, xk is decreasing or increasing, you can't figure it out. But there is of course some correlation. So whenever it's on the diagonals, then you can say that, so in these four figures, you can say that there is some correlation between xi and xk. So exactly in this case, there is negative correlation because as the xi is increasing, xk is decreasing. And if you observe this case, as xi is increasing, xk is also increasing. Because if you observe here, xi is taking smaller value and xk is also taking smaller value. And if I increase xi value, so here you can see, so xi value is larger and correspondingly proportionally xk is also increasing. So they are moving in the same direction. So can I say that there is a positive correlation between these two variables xi and xk? So that's how you can define correlation. And now consider this case, there is no correlation at all. So xi and xk, there is no relation at all. So how can you say that? So that so here you can't say that. So when xi is taking some value, you can't give any inferences related to xk depending on xi. So there is no correlation at all. So now let's see the probability distributions. So probability distribution basically, so it's a statistical function which gives you all the possible values for a random variable and all the possible likelihoods of a random variable, and this is shown in the graphical representation. That's what is called as probability distribution. So now let's take an example for, so the sum of two dice, the values, the sum of, so you are tossing basically two dice, and what is the possibility of some values? So you can, the sum value on these two dice can be either a 2, because so for each die, so the possible values are, so 1 to 6, right? So the second value, so it's also 1 to 6. And so what is the possible values for the summation of these two dice? If you consider, so it is varying from 2, 3, it's 2, 3, 4 and so on up to 12, because 6 plus 6 is 12. So that's the range of values that the sum can take when you throw two dice. And the probability, if you consider the probability of getting 2 when you throw two dice, the sum of the two dice is 2. In that case, the probability is 1 by 36. So that we are representing here. And likewise, we are representing the probability of every possible value for the random variable. So that is what is represented with the distribution, probability distribution. And the probability distribution can be of discrete, can be of continuous also, as we already discussed. So in the previous case, in this example, so the random variable is taking discrete values. So this distribution is called as discrete distribution. And say for example, I am referring to some continuous value for the random variable. In that case, your distribution will become continuous distribution. So now we'll see some of the distributions. So we'll discuss in detail about Bernoulli distribution, binomial and the Gaussian distributions. So these two will consider for the discrete case, and Gaussian distribution, of course, you can use it for discrete case also, but we'll be considering that for the continuous distribution. So let's see what the Bernoulli distribution is. Bernoulli distribution is basically a discrete distribution, and the possible outcomes in this case are 0 and 1, and the parameter in this case is mu. So try to follow this very focused way, so otherwise you cannot get the next class. So the parameter for this Bernoulli distribution is mu, and the possible outcomes are, whenever there is the possible outcomes are 0, 1, yes or no, true, false, in that case only such distribution comes under the Bernoulli distribution. Such distributions are called as Bernoulli distributions. Now consider the example of flipping a coin and getting a head. So when you flip a coin, then the possibility of getting a head. So either it takes a 0 or 1, right? So that's why you can consider this as a Bernoulli distribution. So here I am taking the coin is a biased coin. That's why getting a head, the probability of getting a head is 0.6, and when the probability of getting a head is 0.6, in that case the probability of getting a tail is 0.4, and so the probability of success I consider it as 1, and the probability of failure I consider it as 1. So that is how the Bernoulli distribution is defined. And in case of the Bernoulli distribution, the distribution can be defined as, given random variable, given this parameter, the distribution is defined as mu power x into 1 minus mu power 1 minus x. So that is how Bernoulli distribution is defined for any random variable given the parameter. We already discussed that this is having the parameter mu. And now the mean in this case is equal to mu, that is expectation of x, and the variance of x is defined as mu into 1 minus mu. So you must have studied all these things in the 10th standard or +1 or +2, but just kind of review, we are discussing all these things. And now let's see what the binomial distribution is. So you can consider binomial distribution as a generalized version of the Bernoulli distribution, and of course it's also a discrete type of distribution because the number of possible outcomes are known. And here the number of possible outcomes are no more binary, they are an integer. So when the number of possible outcomes are more than 2, then you can go for the binomial distribution. So here I am considering m as a number of parameters, m as a number of possible outcomes, and the parameters possible are, so n is the number of trials. So out of these number of trials, what is the possibility of getting 2 heads, 3 heads, so on and so forth. And mu is the probability of getting success. So these two are the parameters of this case. And now consider the example. What is the probability of flipping heads m times? And out of n independent flips, what is the probability of getting m heads up? And given the probability, given the success probability as mu. So you will be given your mu, and so n is also given, and you need to identify m. So you will be given the probability mu, and you will be given, so out of n samples, what is the total number of times the experiment is done, that's the n value, and you need to identify how many times, what is the probability of that, what is the probability of getting head m times. So you can consider this here itself, you can understand the probability of getting that is varying from 0 to 12 in this case. So when n equal to 15 and the probability of 0.2, for that I have taken the distribution and I have drawn this. So this is what the distribution sample for this example. And now the Bernoulli distribution can be represented as, for a random variable, so m given n comma mu is defined as, so m into mu power m into 1 minus mu into n minus m. That is how you can define it. And mean of the random variable can be defined as mean equal to m into mu. And similarly, variance can be defined as n into mu into 1 minus mu. So the only difference between binomial and the Bernoulli distribution is there is no n, here you got an n because you are repeating the trial for the same trial for n times. So now let's see what Gaussian distribution is. So Gaussian distribution is very, very important to understand because we assume that, so whatever the experiments you are doing, So in your pattern recognition systems, so you are making the assumption that so the data follows the Gaussian distribution, because always the real world data follows the Gaussian distribution. I'll give you an example at the end of this session. So let's try to understand what Gaussian distribution is. So it's also called as the normal distribution, and it's widely used distribution for the continuous variables. In the continuous case, this is the most widely used distribution, and most of the real world data follows the Gaussian distribution. If you understand what Gaussian distribution is, then you can understand so how we say that most of the real world data is following Gaussian distribution. So now in this case of the single variable case, because there is a possibility of single variate and a multivariate case also. So that's why we consider single variate case. The Gaussian distribution case, the Gaussian distribution of a variable can be defined as, so this is the symbol for the Gaussian distribution, n. So x comma, so or you can even write it as x given or x colon, both are the same. So the variable, the probability that x given, mu comma sigma. So here the parameters are mu and sigma, where mu stands for mean and sigma stands for the standard deviation. So please try to focus on this, it's very, very important. And this can be defined as 1 by square root 2 pi sigma square into exponentiation of minus half into x minus mu whole square by sigma square. So that is how in the single variate case the binomial distribution is defined. And in this case, mu is a mean, sigma square is a variance, and sigma is a standard deviation. And the mean of the Gaussian distribution is defined as expectation of x. Actually, this is wrong. So we'll see at the end of the lecture, or you can even say that so sigma equal to 1 to n inside. It's 1 by n into. So that's how the mean is defined. Similarly, the sigma is also defined as 1 by n into sigma equal to 1 to n. Psi minus mu. So this is how sigma is defined. So here you can see that so this is the mean of the distribution. So this is the mean of the distribution, and this you can see the width of the distribution. So this is an example for the Gaussian distribution. Always the Gaussian distribution looks like a smooth bell curve. So if you observe the previous case, so here you can't see any bell shape, right? And so none of the other distributions follows this kind of bell curve. So this bell curve is a popular kind of distribution where your data is following. So your mean is here, and so on both the sides you have equal amount of data. So that kind of distribution is called as Gaussian distribution. So for your convenience, I have given some examples of Gaussian distribution. So here you can see this is the curve which indicates this mu value is 0 and your variance is 0.2. So because your variance, the width of the curve is very small, right? So that's how your variance is very small, and the mean, if you observe, where is the mean? So here the mean is 0. So the distribution whose mean is 0 and standard variance, so such distributions are called as standard normal distributions. So here this is the example. With mu equal to 0, which one? This red one. So with mu equal to 0 and the variance is 1. So that means the standard deviation is also 1. And similarly, you can observe the orange shaped curve, so which is almost flat, but still it's having the bell shaped curve. So both the ends, it grows in the same way. So that's why it forms the bell shaped curve, and such distribution is called as the Gaussian distributions. And you can even see here the mu value is -2 and the standard deviation of 0.5. And if you consider the weights of a person, so usually how the weights of the person is, so I said that, so I have given the clue that most of the real world problems follows the Gaussian distribution. So now let's see, so let's try to justify that statement. So consider the weights of the person. The random variable is basically representing the weight of a person. So what is the mean weight of the person? The mean weight of the person would be something like 70, right? And if you consider, so the range of the weights of the persons would be something like 2. And if you observe, most of the examples are close to the distribution, and when you go away from the distribution, so the number of examples will be very less. So this kind of distribution is formed when you consider the weight of the person, even height of the person, or the temperature of the day. So that is how. So this is the distribution. So this is the mean value, and if you see, so most of the values are close to the mean. And when you go to the extreme values, so how many people would be there in the world with 500 kg of weight? So hardly no, right? So even if they are there also, 1 or 2. So you can even, it's insignificant. So that is, the values that are close to the mean are high, and when you go to the extreme values, the values are insignificant. So such kind of distributions are called as the Gaussian distributions. And now, so you are convinced that most of the real world problems, the data follows the Gaussian distribution. So that's why it's very, very important for us to understand. Now let's see, so in the previous case we have seen the Gaussian distribution for the univariate case. So in case of the univariate case, this is how you can define the Gaussian distribution. So the parameters are mu and sigma, and given this variable, the random variable, so then the probability of x given mu and sigma can be defined as 1 by square root 2 pi square exponentiation of minus half into x minus mu whole square by sigma square. So when your x is a scalar, then you can represent that. So that is a single variable x. But when your x is representing multivariate, in that case, that is, can be a vector also, right? So in that case, how do you define this? Gaussian distribution is, so this is how you can define it. So your sigma will not be, so the variance will not be there, right? So now your covariance matrix sigma comes into picture. So this can be defined as 1 by 2 pi power e by 2. So sigma, the determinant of the covariance matrix, so whole power 1 by 2 into exponentiation of minus half into x minus mu transpose into sigma inverse into x minus mu. So that is how the Gaussian distribution is defined. The density function is defined in case of the Gaussian distribution for multivariate case. So here D stands for the dimensionality of this variable x. So this is for the multivariate distribution, right? So in case of the multivariate, your x represents more than one value. And how many values are there to that? So that is the dimension thing. So here the sigma is the covariance matrix of the data, and this pipeline symbol indicates the determinant of the covariance matrix. So while discussing the matrices, we discussed what covariance is, how to identify covariance. So now, determinant. So the determinant of the matrix, and take the square root of that, and exponentiation of minus half into x minus mu into sigma inverse into x minus mu, or transpose into sigma inverse into x minus mu. So that is how you can define the Gaussian distribution in the multivariate case. So up to 3-dimensional can be visualized, and more than that it cannot be visualized. So I have given one exercise problem for you to solve. So try to go through the problem and try to solve it using one of the techniques that I have discussed in this lecture. And of course, I have given the solution also for that. So in today's class, we have discussed what probability is, and I have given detailed intuition of why probability is required for the pattern recognition systems, and what are the random variables, and what is conditional probability, and the most importantly, what Bayes theorem is, and to solve what kind of problems Bayes theorem can be used. And in addition, we have also seen discrete distributions and the continuous distributions. So when you can call for which kind of problems, so you consider them as continuous distributions, and which kind of problems you can consider them as discrete distributions. So with real-time examples, we have seen all these things. We have discussed, right? So then in addition, we have discussed Bernoulli distribution, then what are the parameters, so then binomial distribution, what are the parameters. So all those things we discussed in this lecture. So those who are comfortable with the probability and statistics, they can skip this video. So thank you for watching the video. So let's meet in the next video.